an average day, you read and write many documents and emails, view or even upload pictures and videos. In this presentation, we examine how text, sound, images, and videos are captured, processed, stored, and transmitted. We see images when light hits our eyes, hear music when sound waves reach our ears, and taste the chocolate when we bite the cake. Computers, on the other hand, can only process an electrical signal, nothing else. This means that we need a way to convert our real-world information of documents, pictures, and songs into electrical signals which can be processed by a computer. Modern devices use sensors like microphones, cameras, and scanners to capture real-life data and then code or digitize the data that is captured. The basic idea in coding is to take real-world data and convert it into a stream of electrical signals which can be represented as a stream of zeros and ones. The decimal numbering system uses 10 digits, 0 to 9, to represent any number. A numbering system that uses only 2 digits, 0 and 1, to represent any number is called a binary system. In both the binary and the decimal numbering system, the place of the digit in the number determines the value that it represents. For example, in the decimal system, the digit 5 in the number 500 represents 5 100ths, while the 5 in 50 represents 5 tenths. A binary system of 0 and 1 can represent the computer world of electrical pulses. A single electrical pulse is represented by a 0 or by a 1 and is called a bit. A group of 8 bits is called a byte. When discussing large amounts of bytes, we use K or kilo for thousands, M or mega for millions, G or giga for billions, and so forth. The early digital codes were deployed for keyboards. A unique code for each letter, number, and other keys enabled the capture of keyboard strokes. The code had to include uppercase, lowercase numbers, special characters like comma and a dollar sign, as well as keys such as escape, page down, home, etc. In the early days, computer companies implemented different codes. As a result, there was no standard keyboard, and data transfer between different systems was a complicated task. In 1963, the American Standard Association published the ASCII code, a code that is based on 1 byte or 8 bits to represent all characters and keys on a keyboard. The same year, AT&T adapted the code for the teleprinter network, and 5 years later, in 1968, President Johnson mandated that all computer systems sold to the federal government are ASCII compatible. Since then, ASCII is the standard code for all alphanumeric information, including word processing, text messages, and touchscreen keyboards. Every time you press a key on a keyboard, a byte representing the ASCII code of that key is sent to the computer. Coding sound is a little more complicated. Microphones capture sound waves and convert them into an electrical signal that shows both the strength and frequency of the sound wave. The signal can then be used to regenerate the sound via a speaker. This is the underlying technology for records, tape recorders, and other analog devices. Analog means a continuous signal without interruptions. The challenge is to convert an analog signal into a digital sequence of zeros and ones. The solution is based on the idea of kerr-fitting or smoothing algorithms, which you might have learned about in your statistics courses. The analog signal is sampled many times, and then the sampled data points are used to create an approximation of the original data. Specifically, when digitizing a sound signal, it is measured at different points of time, say every second. Each measure generates a value to represent the sound. This value is then coded as a sequence of zeros and ones. These value points can be used to generate a line that is an approximation of the original sound wave. You can think about this process of regenerating the sound wave from the stream of zeros and ones as the process of connecting the dots. How often should the sound be sampled? Think about a line that represents changes in temperature over a week. This is a continuous line. A temperature changes gradually, and there are no breaks in the line. If we take 2 samples, say the beginning and end of the week, it is apparent that we do not have enough data to generate the original function. If we sample the data daily, then the regenerated function is a little better than a sample of 2 points, but not accurate enough. Obviously, midnight temperature samples do not reflect the temperature during the day. If we sample the temperature every hour, then in a course of a week we collect about 170 data points, which yield an approximation that is closer to the real line. A sample every minute provides over 10,000 data points. When connecting the 10,000 points, the approximation is very close to the original line. In summary, a larger sample yields a better approximation of the original signal. First commercial implementations of digitized sound were for the long-distance telephone network. The sound was sampled 8,000 times per second and was coded with an 8-bit binary number on a scale of 0 to 255. This sampling generated data at the speed of 64,000 bits per second. The concept did not change over time. Sound quality has improved with better accuracy, more sampling, and the use of 16 or more bits to code each sample. Nowadays, standard music recording is done at the speed of 128 kilobits per second. High-quality systems may record or produce a stream of 320 kilobits per second. For example, sampling at 128 kilobits per second of a 5-minute song generates over 38 million bits, or almost 5 megabytes. Digital cameras and other imaging devices use sensors that divide the image into a grid of many small dots. The sensor captures each dot on the grid and codes its color and brightness. A finer grid means that a larger number of dots are captured, and consequently it supports regeneration of a finer image which is closer to the original. An image that is regenerated from a grid of 10 million dots, also called pixels, is of better quality than an image that is regenerating for 1 or 2 million dots. Similarly, using 24 bits to code color and brightness generates a much higher quality image than, say, using 8 bits, as it supports more than 16 million versus 256 tones and shades. The size of a digital image is measured by the number of dots or pixels, not in inches or centimeters. If a picture's size is 1800 by 2400 pixels and it is printed on a 6 by 8 inch paper, the density or resolution of the print is 300 pixels, or dots per inch. This is also known as DPI. Project the same image on a screen that is 120 inch by 160 inch, and there are only 15 pixels per inch. Most computer monitors show about 100 to 120 pixels per inch, and good quality prints are at 300 DPI. Movies are made by a series of pictures known as frames that are presented in a rapid pace of about 30 frames per second. Digital movies are large in size and until recently required special equipment for recording. Modern video webcams are capable of recording high-definition movies. However, high-definition movies store a large amount of data. Transmission of sound and movies require a steady stream of bits. If the stream is too slow, sound or video will freeze and wait for the missing bits. Therefore, many web users prefer small format and lower quality video for chat and other interactive applications. Finally, we should understand compression. Compression is a coding technique that allows a reduction in the number of bits stored or transmitted with minimal impact on quality. The main reason for compression is to improve the utilization and reduce cost of resources like storage and communication lines. Known compression algorithms are JPEG for images and MPEG for video. The ability to digitize data is the foundation for modern information technology. If it can be digitized, it can be processed, stored, and transmitted.